Okay. Hey people, so I've got some interesting housekeeping for once. Next, middle of next week, the NTEU, the National Tertiary Education Union, is calling a 24-hour strike. I'll be part of that. Won't go into huge detail about grievances with that. I'm not going to complain about my job. I've got a pretty good gig here overall. I'd like it to stay like that, of course. But in particular, the union's really serious about trying to make life a bit better for sessional workers here. That includes your TAs, for example, who at the moment, for example, do not have any access to sick leave if they're sick, all this sort of thing. If you want to look into it, I'll probably try and post something on Moodle or something, but you can see the sorts of claims the union is after. I think it's important stuff to support. So that's the rationale. That will mean, seeing as we don't have any seminars in there, either fortunately or unfortunately, the only big effect as far as this stuff goes is that I won't be answering emails or forum posts in that period, because I would like to be available to answer emails and forum posts just before the first assignment is due. I'm going to knock that back one day. So you've got one more day for assignment one, which will mean if you email me on Thursday afternoon, I can actually reply, which won't be the case on Wednesday. Does that make sense to everyone? If you have an applied class in that period, probably it'll still be on, right? A couple of our TIAs are union members and may also decide to strike. If that's the case, they will email you and let you know, and we'll organise some make-up classes. But unless you hear, assume applied classes are still on in that period. Okay, Quiz 2 comes out tonight. I may have stuffed up that due date. Actually, I'm not sure I updated that. It's due on Wednesday, not next Wednesday, the Wednesday after, right? Whatever that is. 27th, yep. I thought I stuffed that up, yep. Sorry, 27th. I will fix that. Solutions to Cheat Sheet 2 and hints for practice question 2 will also be available tonight, and solutions to quiz 1 will be available on Tuesday. Okay, so let's get on to what we're here for. So, we're talking about induction today, and induction is sort of the go-to proof method for proving things about recursive algorithms and structures. And obviously, recursive algorithms and structures come up a ton in computer science, right? Sequences, but also, you know, trees, all sorts of things, and obviously also recursive algorithms. So, particularly useful for proving things that involve recursive algorithms, strings and similar data structures, trees and similar data structures. You could add to those. So it's a very computer science-y method of proof, I would say, and very important to have an understanding of this if you want to understand how recursive sorts of things work. Okay. So, I don't want you to follow what I'm about to say in super close detail, but feel free to. But I'm not going to try and get that happening. What I want to do is begin by just giving you a vibe of why we might want a proof method like induction, right? We'll go into much more formal, much probably easier examples later, but for the moment, let's get a vibe of why we might want this. So imagine we've been asked to prove that the sum of the angles in a convex n-sided polygon is this many degrees. Well, I've forgotten to sort out my clicker. Very sad. Where are we? Couple of little definitions here. Polygon's just a 2D shape with straight sides. Convex means that it's sort of fat, right? A bit like a circle. If you draw a line between two corners, it's inside the shape. You don't have to worry about the details here. So, you probably already know, and we're going to take as given, one case of this, right? The sum of the angles in a triangle is 180 degrees, which is what this says for n equals 3. Right, so how would we go about proving this for shapes with more sides? What could I do if I've got a shape with 4 sides and I know how triangles work? Yeah, chop it in half, right? If I chop it in half like that, then I can say red angles add to 180, blue angles add to 180, so all the angles add to 360, and that's what I needed to prove for 4, right? 180 times 4 minus 360 is 360. So a 4-sided shape has 360 degrees as the sum of its angles. What if I had a 5-sided shape? I could chop it up into 3 triangles. Let me do it a slightly different way. I could chop it up into 1 triangle and a 4-sided shape, right? Sum of the angles in the triangle is 180. We just showed that the sum of the angles in the 4-sided shape was 360, right? So the total sum of the angles is 180 plus 360 is 540. That's what I wanted to show for n equals 5, right? What'll I do with the 6-sided shape? I can chop it into a triangle and a 5-sided shape. I know this is 180. I know this is 540. So I get 720, right? And hopefully at this point you're sort of starting to believe that this is really true and also that we've basically proved it, right? But of course, if you were really strict and formal, you'd say, well, no, you've proved it for 3 and 4 and 5 and 6, but how do I know it's true for 100? Right? And the question is, do we really have to go through 99 or 97 or whatever of these steps to prove it for 100? Right? So we want to say, and blah, 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 this works. Right? And induction basically is a way of formally saying, blah, 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 this works. That's the concept of it. So how does it formally do that? Well, instead of doing this as a series of jumps, right, we go from 3 to 4, we go from 4 to 5, we go from 5 to 6. What it does, again, this is quite a sort of a program-y type approach. What it does is says, why don't we prove a general way of going from any number to that number plus 1, right? So how would this actually work? Well, what we would say is let P of n be the predicate, that the sum of the angles is 180n minus 360. We show it's true for n equals 3. That's our triangle rule. Now we make a general step. So instead of going from 3 to 4, or 4 to 5, or 5 to 6, or 78 to 79, we go in general from a k to a k plus 1. And we say, suppose that we've already proved all the way up to k that the sum of the angles in a k-sided figure is the right number. Now let's prove it for k plus 1. Well, we can split a k plus 1 convex polygon into a triangle and a k-sided shape. Sum of the angles in the triangle is 180. Sum of the angles in the k-sided polygon is this, because we're assuming that we've already gotten that far in our proof. And then we get one step further, right? We get one more thing. Again, I'm not wanting you to follow this closely. This is just to get the vibe, right? And because we've done it for a small value and we've done a general increasing step, we now actually have it for everything. So that's the vibe. That's what induction does. It promises to stop you having to do this a million times to prove it for an a million-sided shape or whatever, right? Okay. So let's see this in a whole lot more detail. So basically, somehow, one of the key reasons, or perhaps the key reason, why induction works is because you can get to any natural number. So let's say the natural numbers are 0, 1, 2, 3, blah. You can get to any natural number by starting with 0 and adding 1 some number of times, right? Might be a lot, but you can get anywhere by starting with 0 and adding the right number of 1s, right? And that means that if we can prove something for 0, and also if we can prove that if it works for a number k, any number k, then it works for that number plus 1, then we've proved it for everything. And people often go to analogies with dominoes here. I think the pre-watching video did that. You know, if you can do it for 0 and then you can show that any domino knocks over the next domino, then you get all your dominoes, right? So proof by induction works by proving the required property is true for 0, or in general for whatever the first thing we need is, and then showing that if it works for some number, it works for that number plus 1. Okay. So this is just what the last thing said. We prove P of 0 is true. That's called the base step. P of n here is a statement, right? It's a true-false statement. You can think of it like a predicate. We prove it's true for 0. That's called the base step. Prove that for each integer greater than or equal to k, 0, k greater than or equal to 0, if it's true for pk, then it's true for pk plus 1. And so the idea is it's true for 0, but we know if it's true for 0, it's true for 1 by our induction step, right? So we get it for 1, but then we know if it's true for 1, it's true for 2 by our induction step again. So we get it for 2, and so on and so on and so on. You just keep knocking over dominoes or doing whatever. Generally, we prove the induction step by assuming pk is true for some fixed arbitrary k and proving that pk plus 1 is true. And people often find that a bit dodgy, right? It sort of almost feels like you're assuming what you're proving. But I think the reason, in my head at least, why it's legitimate is because you're making that assumption just for the purpose of proving this if-then statement, right? So you're not assuming it's true for all k or whatever. You're just saying if it's true for 1, then it's true for the next. And then the thing that then bails you out is because you know it's true at the beginning, then you do get it all the way through, right? Any questions on the basic concept there? Yeah?
The base step, is it really necessary?
Absolutely. So the base step is definitely necessary because if you think about it, I mean, if-then statements, false implies anything, right? So we could have a legitimate proof that if it's true for k, then it's true for k plus 1, but if it never starts working, then you don't get it anywhere. So base step is really necessary, yep.
And then if we had started our base step as like n equals to 2, does that mean our proof is only for k is equal to or greater than 2?
100%. So the statement was if we start at n equals 2, then the proof only works for k greater than or equal to 2. 100%, but it does work for all k greater than or equal to 2. So yeah, exactly. Okay. So another analogy is, you know, if you can get your robot to step 0 and you can program your robot to climb from step k to step k plus 1, then your robot can climb as high as it likes, right? If you've got a generic step climbing algorithm, single step, but from any step to the next one, then you can go up any flight of stairs, right, as high as you like. Okay, so let's see, we'll see a couple of examples of this, and then I'm going to ask you to sort of do one of these by flux, but let's see some examples. So with a couple of these, you could definitely prove them other ways. The point is to learn how to prove them by induction, right? So this one, you could probably prove it using mod 3 congruences if you wanted to split into cases. Okay, so let P of n be the statement 3 divides n cubed plus 2n. I'm going to say this a million times in this lecture, but P of n is not n cubed plus 2n, nor is it 3. It's a yes-no statement, right? It's a predicate. Okay. So this statement for n equals 0 is saying 3 divides 0 cubed plus 2 times 0. So 0 cubed plus 2 times 0 is 0. 3 definitely divides into 0, right? Because 3 times 0 is 0. So P of 0 is true. So we've got a base step. Okay. So the induction step. So let k greater than or equal to 0 be a fixed integer. So this is where we're starting, right? So we need k greater than or equal to 0 because we could be starting on step 0 or on step 1 or on step 2 or on step 3, right? This put our robot on step 0, if you like. We need to now show we can go from any step bigger than 0, 0 or bigger rather, to the next step. Okay, let k greater than or equal to 0 be an integer, and suppose that we already know our statement is true for that integer k, right? So we're assuming that 3 divides k cubed plus 2k, which is the same as saying k cubed plus 2k is 3 times a for some integer a, right? Okay, we want to now prove, we've assumed that p of k is true, we want to prove that p of k plus 1 is true. Now p of k plus 1 says 3 divides k plus 1 cubed plus 2 times k plus 1. So in other words, we need to show k plus 1 cubed times 2k plus 1 is 3b for some integer b. Making sense? Okay, so k plus 1 cubed plus 2k plus 1, well, that I can expand out like this, and it equals this. Now, if you think about it, I have some useful information here, right? I know pk is true, which means I know that k cubed plus 2k is divisible by 3. So let me use that information. I'm going to pull a k cubed plus 2k out of here. I know this is divisible by 3. So now I've just got to show what's left is divisible by 3. But hey, look at that. What's left looks pretty divisible by 3, right? So I can say this is 3a, right? That was my assumption. K cubed plus 2k is divisible by 3. That's 3a. This is a whole bunch of 3's, right? So I get that this thing is 3 times a plus k squared plus k plus 1. All I care about a plus k squared plus k plus 1 is it's an integer, right? So it's my b, and 3 divides this. So I've proved k plus 1 is true. I've proved if I have pk, then I have pk plus 1. And because of that, I've proved that the statement is true for every integer n greater than or equal to 0. Yeah.
When you're doing the thing with the I,
Mm-hmm.
why not try to just put like where I is an element, you said?
Yes, you could just say where a is an element of the set of integers. That's the same as saying for an integer a. Yeah, yeah. Okay. Cool. Okay, so there's a proof by induction. We've seen one. Let's see another one. So again, this is a really obvious statement, right? If I've only got the letters A and B, and I've got to make a word out of A's and B's, then the number of words of length n should be 2 to the n, right? Each time I have 2 options. But let's prove that really formally by induction. So, P of n can be the statement there are 2 to the n letter words using the letters A and B. Right? Again, P of n is not 2 to the n, right? It's not a number, it's a yes, no, true, false statement. Okay. So, we first want to prove a base step. Now here, what we want to prove starts at 1, so we're going to prove that P of 1 is true. And P of 1 says that there are 2 one-letter words using the letters A and B, and that is the truth, right? There's A and there's B. So 2 one-letter words, A and B, so P1 is true. Okay, induction steps. So fix an arbitrary integer k greater than or equal to 1 now, right? Because we started our robot on level 1, we need to show we can climb from level 1 to level 2, but also 2 to 3, and so on and so on. So, let's suppose that P of k is true. What does that mean? That means that there are 2 to the k letter words using A and B, right? Now, we want to show there are 2 to the k plus 1 letter words using the letters A and B. Well, a k plus 1 letter word, what are the possible letters it can end with? A or B, right? So it has to be WA or WB, where W stands for a big long K letter word, right? So my K plus 1 letter words, each of them can be formed by choosing some W and A or some W and B, right? So there are 2 to the k words that I can write as WA because I have 2 to the k choices for W, right? That's my P of k. P of k told me I have 2 to the k choices for a k letter word. Same deal, 2 to the k words that can be written WB. So how many in total? 2 to the k plus 2 to the k is 2 to the k plus 1 letter words. And that's what I wanted to show, right? That's my pk plus 1. And so P of n is true for every integer n greater than or equal to 1. Yeah?
Does that mean that if you wanted to prove for all integers, you just do base case of 0, and you do proof for n plus 1, or like k plus 1, and then you do a second induction step for k minus 1, so it goes both sides?
Okay, so the question was, if I wanted to prove something for all integers, both positive and negative, then could I do a base case of 0 or whatever and show that if k, then k plus 1, and if k, then k minus 1? And yep, that would 100% work, because it would really, I guess, arguably be 2 separate inductions, one showing it's true for all non-negative integers and one showing it's true for all non-positive integers, but that would definitely work, yeah. Okay. So, the notes have pointed out something that we've already seen. There's nothing magic about 0, right? If you want to start a induction at 7, that's totally fine. You just prove a base case for 7, prove that for an arbitrary integer k greater than or equal to 7, you get k plus 1. P of k implies P of k plus 1, and you're set, but of course that only tells you it's true for n greater than or equal to 7, right? So, good. Okay, so question 9.1 in the notes is, I guess, pointing out that often if you're trying to prove something by induction, you have to sort of see a pattern or whatever first, at least if you're trying to figure out what you want to prove. So we'll just do a little bit of, well, it'll be a break from the induction. So what's the pattern here? So x divides n squared plus n. Here are the values of n squared plus n. What's the best x we can do here? Probably just 2, right? They're all even, but given there's a 2 here, we're not going to necessarily see other common factors. So you could definitely prove n squared plus n is even by induction. It's a good exercise to do if you want to do it. Okay, the sum of the first n odd numbers is x. So we're actually going to prove this a bit later in the lecture. You're going to help me. But what's our pattern here? 1 gives us 1, 2 gives us 4, 3 gives us 9, 4 gives us 16, x squared. Yep, totally agree. X is n squared, sorry, yep. Okay, slightly trickier one, that this slightly complicated fraction is 1 minus x. I've done the hard work for you, hopefully. Yep, so 1 on n plus 1, right? For 3, this is 1 minus 1/4. For 4, this is 1 minus 1/5, and so on. So any of them are good exercises to do if you're feeling like doing some induction. Okay. So here's an example of one where we really do have to start our base step higher up, right? If you look at this, notice it's not true for n equals 3, right? For n equals 3, this is 6 and this is 8. So we can start at 4, but we can't start lower than that. Okay, so P of n is the statement n factorial greater than 2 to the n. Are you sick of me saying this yet? P of n is not n factorial, it is not 2 to the n, it is a true-false statement, right? Okay, so let's prove our base step, which is P of 4. Well, again, separate your left-hand side and your right-hand side when you're doing this. Don't write down that, and because it's then very tempting to start assuming it, right? 4 factorial is 24, 2 to the 4 is 16. So this is true for 4. Okay. So our induction step, pick an arbitrary integer, k greater than or equal to 4, and suppose that P of k is true. So suppose that k factorial is greater than 2 to the k for that k. We want to prove P of k plus 1 is true. In other words, we want to show that k plus 1 factorial is bigger than 2 to the k plus 1. Okay, so k plus 1 factorial, how can we usefully write that? Yeah. Yes, totally agree. So I should have said, obviously, n factorial means n times n minus 1 times n minus 2 times all the way down to 1, right? And the point made there, which was the perfect one, is that that means that k plus 1 factorial is just k plus 1 times k factorial, right? Because this is k plus 1 times k minus 1 times all the way down. This is k plus 1 times k minus 1 times all the way down, right? So very natural sort of inductive thing to do here. Okay, so what do we know about k factorial? Well, thanks to our assumption of p of k, we know it is bigger than 2 to the k, right? So we can say this is at least k plus 1 times 2 to the k, and at this point, this is sort of really good news for us because we only need to show it's bigger than 2 times k plus 1, right? 2 times k plus 1 is 2 times 2 to the k. We've just shown it's bigger than k plus 1 times 2 to the k. In particular, k is greater than or equal to 4. So we've shown it's at least 5 times 2 to the k. So we've got definitely that it's bigger than 2 times 2 to the k. And so we've got that it's bigger than 2 to the k plus 1. We've got what we want. And and this, of course, this step here was using p of k, and this step was using k is greater than or equal to 4. So we've got what we want, and we've got this for every integer n greater than or equal to 4. Question here.
Sorry, and is k factorial bigger than 2 to the power k? It's not bigger or equals to. Are we still able to use 2 to the power k to substitute it in?
That this is strictly, k factorial is strictly bigger than this.
Yeah, but it's not bigger than equals to. So
But that's an even stronger statement. If we're saying it's strictly bigger than, I mean, it's certainly greater than or equal to if it's greater than, right? Yeah. But I mean, what we're doing is we're saying because this is strictly bigger than this, when we multiply by k on both sides, we still have that strict inequality.
so it's not bigger than but okay, no.
Yeah. That makes some sense. Was there a question there? Okay. All right. So, I've got a whole bunch of flux exercises for you now. So I'm not going to ask you to do this all in one hit, but let's try and together go through this. So, how do we start? So, your options are here. How do we start this proof? So hopefully you can see the answers on your screens, so I'll go back to the slides for a second. So this is proving that the sum of the first, what we saw before, the sum of the first n odd integers is n squared, or the way it's phrased here, the sum of the first n plus 1 odd integers is n plus 1. Okay, so we're going to have to go through these fairly fast, so I'm going to make you answer in the next 10 seconds. Okay, good. Good, good, good. So P of n, we always want this to be a true-false statement, right? In this case, it's this equality. We don't want to have it equal to the left or right-hand side. That's not the best way to go about this. Okay, so good. So that's our statement P of n. Next question, how do we do our base step? I've obviously in the flux done these as fairly abbreviated things. I'll do them a bit more properly on the slides. Another 10 seconds or so. Okay, good stuff. So, two important things here. Our base step needs to be for 0, right? We're starting this, we're being told to prove it for 0, so our base step needs to be for 0. That means that this guy and this guy are not so good. And this one is the wrong way around, right? You don't want to start by assuming P of 1 is true and then get down to an obvious statement. You need to do the opposite of that, right? So best to split into a left-hand side and a right-hand side. So phrased slightly better than I did in the flux, we would say the left-hand side of P naught is 1 because it's just 1 plus blah, 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 up to 1. That's just 1. The right-hand side is 0 plus 1 squared is 1. So these are equal and P naught is true. Okay. So next question. How do we start our inductive step? So okay, another 20 seconds. Good stuff. Okay, so really important here, we want to do the first of these and not the second. I know they look a little bit similar. You're definitely right that k greater than or equal to 0 is the right thing to do. But we're not assuming this for a whole bunch of different k's, right? Certainly not assuming it for all k's, because if we're assuming it for all k's, then we'd have what we wanted anyhow, but we're not allowed to do that, right? What we're trying to show is for a specific k, for a specific step, if we can get to that step, then we can get to the step above it, right? And so for that, we need to pick a step first and then assume it for that specific step, then prove it for the step above that. Does that make some sense? Yeah.
Because we've already proven
Yep.
Why can't it be C?
C. Okay, so question was, because we've proved that P0 is true, why can't it be C? It's because the first step we need to make is to show that because P0 is true, which we've just proven, that it's true for P of 1. And that means that our first step has to be P0 double arrows P1, not P1 double arrows P2. Does that make sense? All right. So, doing good. So, let k greater than or equal to 0 be an integer. Suppose that P of k is true. Okay, what next? So we want to prove P1. What is P1? Which of these things? Sorry, P of k plus 1. What is P of k plus 1? I should. So this is based, of course, on our definition of the statement Pn here. Another 20 seconds. Good stuff. Okay, so we need to remember that every n in this thing is replaced by k plus 1. In particular, this becomes 2k plus 1, which goes to 2k plus 3, and this becomes k plus 1, which goes to k plus 2. Right? Okay, so I'm going to say that in slightly more detail here. So, sorry, we've supposed pk is true. That means this. We want to prove pk plus 1 is true. We must show this thing, and of course this is 2k plus 3. And this is k plus 2 squared, as you just told me. Very last one, I think. What do we do now? Very hazy answers. Oops. Show me for touching the scroll wheel. Okay. Yeah, I like that as an answer. So let's see how this goes. So the left-hand side is this, which is, of course, just the sum up to 2k plus 3. But it's useful to me for me to split this up because I know what the sum up to 2k plus 1 is. Right? I've assumed it's k plus 1 squared. So I can split this sum into the sum up to 2k plus 1 plus 2k plus 3. Using P of k, the sum up to 2k plus 1 is k plus 1 squared. Then it's some algebra, right? We get to this, and that is k plus 2 squared. Helps to know where you're going, right, with this stuff. So, well done. We did a proof by induction together. So pk plus 1 is true, and this proves Pn is true for each integer n greater than or equal to 0. Okay. So again, you can, for the last 5 minutes, you can chill out a little bit. Again, this is something I more want to give you a vibe of than the very intimate details. First question, 9.3 in the notes, is just trying to point out to you that you can't always trust finding a pattern that lasts for however long. So it says, is this prime for all natural numbers n? If you check, you will find that it is prime for the first 39 natural numbers. And then it becomes not prime for the 40th, right? And when you think about it, it obviously had to become not prime on 41, because this would be 41 squared plus 41 plus 41, which couldn't possibly be prime, right? But you can't always trust patterns, at least in the early days. Okay, last thing I wanted to talk about in a very vibey sort of way, vibe is my word for the day apparently, was merge sort. So merge sort is a beautiful recursive CS algorithm. And it basically works on the observation that merging two already sorted lists is easy, right? So if I have two lists, each of which themselves are sorted, then I just have to look at these two things and think, which goes first? 1. Now I look at these two things. Which goes first? 2. Look at these two things. Which goes first? 3. Look at these two. Which goes first? 4. These two. Which goes first? 5. 6, 7, 8, right? So sorting a list can actually be quite difficult, but merging two already sorted lists is really easy. And the way the merge sort algorithm works, that needs at most x comparisons, where x is the total number of things in the two lists. So the way merge sort works is it says if your list is length 1, then it's already sorted and I'm done. Otherwise, split the list into two halves and call merge sort on both of those halves. And then, of course, what will happen is that for each of those halves, merge sort will split it into two halves, and it'll keep splitting and splitting and splitting until eventually the lists are sized 1, and then it will re-merge them all, right? Because then after you have these two lists sorted, you just merge them as we did above. So it's this lovely recursive algorithm, splits everything up, then says, okay, these are sorted, and merges into larger and larger sorted lists. So that's the way it works. And with this last slide, I'm just trying to show you how induction can really naturally prove things about recursive algorithms. So you can prove by induction that merge sort works on lists of length 2 to the n, needs at most n times 2 to the n comparisons. So that's true for lists of length 2 to the 0. Length 1, you don't need any comparisons. Now you suppose it works on lists of length 2 to the k. Well, that'd need 2 to the k times 2 to the k comparisons. So if we tried to then use it on a list of double that length, it would split that list into two lists of length 2 to the k plus 1. Now we know that on each of those, it uses k 2 to the k comparisons. And then it needs to sort those using at most 2 to the k plus 1 comparisons based on that. So total number of comparisons, when you go through the maths, works out to exactly what you want it to be. So because the algorithm works in this recursive way, it just makes itself, it's just begging to have induction used on it, right? So again, don't need you to get every detail of that, but classic example of a lovely recursive algorithm and using induction to prove things about it. Okay, people, have a good weekend. Hey,
Can I ask, are we required to show induction hypothesis, or can we just do that as part of the induction step?
as long as things are well explained, I'm not hung up on exactly how it's phrased. I mean, whether you actually say, this is my induction hypothesis, you know, but somewhere there should be a suppose or assume or whatever for a P of K, and, you know, then a proof of whatever. Yeah, yeah.
Thank you.
Yes. Yes, yes. Although that is absolutely true, but you obviously induction does sort of require some sort of ordering. Yes, yes, absolutely. But the point being that it's a slightly more complicated process, which means you have to think a bit harder about what you're doing. But yeah, I mean, if you think, for example, like I could say, suppose that I know this is true for all fractions whose numerator plus denominator is less than or equal to a certain amount, right? And then whatever. So, yeah, what you say is absolutely true. Thanks.